Hello, this is Ahmed Hamida, Professor of Mechanical Engineering. Today we will have our second review of thermodynamics in GR 130 for our second midterm. So today we will have two things. We're going to cover lecture 7 to lecture 13, chapter 5 to 7 in the textbook, single and pools, thermodynamics and engineering approach. Then we will have a sample midterm, which was last year midterm, to solve. So remember, your midterm 2 will be this August 3rd from 11 to 12 p.m. So this will be online. And important problems are lecture problems, especially lecture 11, 12, 11, 12, and 13 problems, homeworks. All the homeworks problems are important, and sample midterm, which will be held today. In lecture 5, we talk about the continuity, the conservation of mass. If it means the total mass in equal total mass out, which is in minus out equal the accumulation in the system. So we have in mass, we have out mass equal the change within a system. That's open system. In the closed system, there is no mass in and out. Mass is constant. Then we define steady flow. Steady flow when the mass flow rates are the same. M dot in equal M dot out. M dot in equal M dot out is equal to rho A V. V is the velocity, A is the cross-section area, rho is 1 over a specific volume. Specific volume can be from a steam table, for example, volume per unit mass. If you have the volume flow rate, like AV, is constant, it does not mean a steady flow. We need the volume flow rate, the mass flow rate to be constant. There is no accumulation in our system. Finally, flow work PV. We have two types of energy, U and PV. We combine them together to be enthalpy. H is U, internal energy, plus PV, flow work, or a specific enthalpy. H equals U plus PV. It's specific internal energy and a specific volume, and we add extra column in our steam table. In section 5.2, we talk about the first law of thermodynamics for open system, conservation of energy. Energy can not be neither created nor destroyed, but transformed from one form to another. We have many forms of energies. So if you have a system, you can have heat. You can have work. You can have mass flow rate. This is the ways that we change the energy of the system. Heat, work, mass flow rate. Flow coming with energy or flow leaving with energy. That's why you will see the equation this way. Q minus W plus sigma mass in. This is sigma mass in minus sigma mass out equals the change in the system, U2 and U1. So we have four forms of energy. Q minus W plus sigma mass in, which is energy, minus sigma mass out, with its energy, equal a change in the system, 2 minus 1. This is the first law of thermodynamics. Heat, we talk about heat addition. Positive is it added to the system. Work done by a system. Positive, it's out of the system. Now it's negative because it's input to the system. So you need to make sure that when you substitute here, if it's input, like compressor, it's negative in this equation. Put it negative times negative, it's positive. Mass in has three forms of energy: enthalpy, kinetic energy, and potential energy. A specific enthalpy, a specific kinetic energy, and a specific potential energy. H P squared over 2 GZ. The same for out. If the problem is unsteady, we have right-hand side, U2 and U1. You have U2 plus, again, V2 squared over 2 plus GZ2, U1, V1 squared over 2 plus GZ2. So we have internal energy, kinetic energy, and potential energy. Again, remember, this only happens if you have unsteady. If it's steady state, the right-hand side is 0. If it's closed system, this will be also 0. So we cannot have a steady for closed system. So We have a very important special case, which is if we omit m1 equal m2 equal m, and m dot n equal m dot out equal 0, and there is no mass flow rate, we can reduce this equation to be Q minus W equal delta U. This is exactly chapter 4. Physics of thermodynamics for closed system. Q minus W equal delta U. There is no mass in or mass out. There is no kinetic energy, no potential energy. There is no mass flow rate in the system. So let's talk about the both, steady and unsteady. Unsteady mean we are emptying a tank, for example. Like the last 3 problems in homework 3. These are very important problems for you. So steady flow, like nozzle, diffuser, nozzle to speed up the flow, diffuser decrease the flow speed. Again, this equation can be reduced if you have a special case, like nozzle or diffuser. For example, nozzle, you don't have work, you don't have power, you don't have anything except you have H1 plus V1 squared over 2 equal H2 V2 squared over 2. That's the very simplified form of first law of thermodynamics in case of open system nozzle or diffuser. So the speed, the flow, the velocity increases at the exit while the energy decreasing. So the total energy remained the same. So this guy was big, became small, but the total energy is the same through the nozzle or through the diffuser. The same for turbine and compressor. Turbine, the flow expand through the turbine, so the energy decreasing, but we get work. So the work, if we assume adiabatic, is just m dot delta H, H2 or H1. Or actually H1 minus H2. Because we have input for the turbine with high energy and goes to low energy. And this is a power output. So remember, turbine is we got work. There is no heat, adiabatic for now. Similarly, compressor is the same equation, can be valid for compressor. But compressor, we pay work to obtain higher pressure. So the equation W dot equal delta H, but the result is reflected in higher pressure ratio between P2 and P1. The same actually for turbine, lower pressure ratio between P2 and P1, exit and inlet for turbine and compressor. For throttling valve, this is exactly the same idea, but throttling valve, we decrease the pressure of the flow. So we have simply H0 or Hn equal H out, H1 equal H2. That's it. We have H1 equal H2 through a throttling valve. Similarly, for mixing chamber, heat exchanger, or pipe and duct, all of them, we apply the first law of thermodynamics to obtain what the change happen in the energy, how the energy changes. But the energy cannot be neither created nor destroyed, but it changes from one form to another. Kinetic energy, potential energy to kinetic energy to flow work to work, and so on. Unsteady is an important problem. We're going to take today in the midterm, sample midterm, a problem similar to the homework. So when we fill a tank or emptying a tank, you have just one input or one output, or even both, but you have accumulation in the system. It's not steady. So we have M2 different from M1, and M dot is not constant. It means you have unsteady flow, transient flow. We have taken a lot of problem in chapter 5. Chapter 5 itself is not enough, because 4 or 5, first law of thermodynamics, we need to have something to tell us how bad we are, how the efficiency look like, how much losses we have. That's why we have second law of thermodynamics. There is a very famous problem when I told you about cup of coffee. If the cup of coffee temperature is 60 degrees and your body, let's say 30 degrees, and the heat transfer from your body to the cup, so your body gets colder, and the energy of the cup getting higher, the temperature getting higher. In front of first law of thermodynamics, that's correct. But second law said no. There is a direction for heat, always from hot to cold. Second law of thermodynamics, we have something called thermal energy reservoir, source or sink. It's a body. This body, the temperature does not change. The temperature does not change. if you give heat or take heat, like river, ocean, atmosphere, ambient, temperature remains constant. This is the main characteristic of thermal reservoir. Heat engine is a device that will convert heat to work. The very famous Venn diagram of that was, we have Q high, and we have heat engine, HE, heat engine, and we have Q low, dump it in that. So these are two reservoirs, and we have work, net out. This is the very famous thing. So this is a cycle, it's a device, it's a system. Rankine cycle, Brayton cycle, we're gonna talk about those later in the following chapters. But as of now, we just have Q high. Some of this power energy goes to network, and some dumping into ambient, non-useful. So we have always Q high equal W net out plus Q low. That's always correct. Even if you replace this with refrigerator or heat cycle, everything will be reversed, but it's still equation invalid. First of thermodynamics. Energy in equal energy out. Kirchhoff law, current in equal current out. Continuity, mass in equal mass out. This is the same concept. There is something important for heat engine. It's called thermal efficiency. Thermal efficiency, any measurement of efficiency or measurement of performance of a system, it's output over input. What I want here, I want work. What I pay here, heat. So output over input. Simple. How much you get from what you paid for. I can pay 100 joule, or what? I get just 50 or 60 or even 40 watt. Efficiency is 0.4, 40%. We have other components or other devices like refrigerator and heat pump. So we have three devices. Heat engine, we talk about it, that we need work. Refrigerator and heat pump are opposite to this. As you can see, the arrows are reversed. So we have Q low, W net in, like refrigerator, or even heat pump. So the same, everything, as well as before, but opposite signs. So Q in and W net in, we are both inputs, and we have Q out. So this is Q out. Again, the same equation is valid. Q high equal W net in plus Q low for either refrigerator or heat pump. However, the measurement of performance is different. So COP, refrigerator, or R, COP, or of heat pump, different from heat engine. In refrigerator, we want Q low. We need the things inside the refrigerator to be cooled down. So our output is Q low. Our input is W net. Can be greater than 1. COP heat pump, actually our output is Q high, our input is W net in. So it's Q high over W net in. If everything here be unit time, so all you need to do, just add dot, 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 the same thing. If everything here per unit mass, so it will be Q small, W small, Q small, Q small, Q, W small, Q small, and everything is valid. Again, Q high equal W net in plus Q low. Exactly same equation as before. So coefficient of performance, again, similar to the thermal efficiency, which is output over input. But here can be greater than 1. This is also always greater than 1. Q high always greater than W net in. In the second part, which is open system, actually, In the second part, we give two statements for the second law of thermodynamics. Kelvin Planck, let's say Kp, and we have Clausius statement, let's say. Kelvin Planck said it's impossible to have this device. Clausius said you cannot have this device. So we have something is missing here in Kelvin Planck, which is Q law. There is no Q law here. Something is missing here, which is network. So Kelvin Planck said it's impossible to have device operate in a cycle. It receives heat from single reservoir and produces network. That's impossible. While Clausius said it's impossible to produce a device that takes heat and dump heat without producing network. It operates in a cycle. Cycle means it started at one state, ended to the same state, initial state. So this is impossible. You cannot just let the heat or the energy disappear. You need to convert it from one form to another. So if this is 100 kilojoule, you cannot say, what? You cannot say, I make it 50 watt without it having an output. That's impossible. Energy cannot be neither created nor destroyed. Both of them are equivalent, are the same. So both of these statements says we need to have the three components for all of the system: Q high, Q low, W net. For heat engine, refrigerator, or heat pump. Heat engine, I want work. Refrigerator, I want Q low. Heat pump, I want Q high. Then we talk about reversible process and irreversible process. Reversible process, that process that go from one place to another and go backward, reverse it without any influence on the surrounding. So if you have a process that has no influence in the surrounding, when you go reverse it, it's a reversible process. For example, if you heat a cup of tea at water and you give it some heat, some of this heat is kept to the surrounding. If you cool this down, you will not get the same heat you paid initially. So you paid 100 watt. When you cool it down, you get just 80 watt. Why? Some of heat go to the surrounding. This is irreversible. So if you reverse the process and getting the same output as you paid initially, this is called reverse. Without influence in the surrounding, this is called reversible process. A reversible process like friction, piston cylinder, unrestrained expansion of gas. Heat transfer. Whenever you have heat, delta T, you have a reversible process. So we talk about Carnot cycle. Carnot cycle has 4 steps, 4 processes. 4 are reversible. 1 to 2 to 3, 3 to 4, 4 to 1. It's a cycle. Go from 1 back to 1. 1 and ended by 1. 1, 2, all of them are reversible. All of them are reversible. This is the most efficient cycle. It's called Carnot cycle. For 1 to 2 is isothermal. Temperature is constant. 2 to 3, adiabatic. We used to say adiabatic and reversible together, isentropic, 0 change in entropy. Reversible, isothermal. That's 3 to 4, finally, adiabatic. So again, isothermal adiabatic, isothermal adiabatic. Let's plot them in the TS diagram, the best diagram ever for this. We started here, expansion, expansion, compression, compression. The first one, temperature was constant, we call it T high. The other one was constant temperature, T low. 1 to 2, isothermal. 2 to 3, adiabatic. Because reversible. That's why it's isentropic. 3 to 4, isothermal. 4 to 1, adiabatic. 1 to 2 is expansion. 2 to 3, expansion. So we have 2 expansions and 2 compression. Reversible, reversible, reversible. Isothermal adiabatic, isothermal adiabatic. This is rectangle. It will be a little bit different in PV or TV diagrams. But this is the best curve. Also, we said that this area how much heat you paid. Q high minus Q low, actually. It's heat, net heat, Q high minus Q low, which is equivalent to work. We have two principles for Carnot. If two Carnot cycle operates in the same temperature, the temperature is the same. Like let's say you have Carnot 1 and Carnot 2. Both of them have the same efficiency if the temperature is the same. If T high is the same and T low is the same, of course they are the same. However, they are operating at different Q high and different Q low, but the efficiency is the same. If any device operates at between T high and T low and is not reversible, irreversible must be lower than eta Carnot. Eta irreversible or eta real, it's 1 minus Q low over Q high. Actually, this is W net over Q high. This Carnot is 1 minus T low over T high, which is actually thermal temperature scale. That Q over Q equal this Q low over Q high equal T low over T high, or Q high over Q low equal T high over T low. This is called thermal temperature scale. This is the efficiency of Carnot cycle, the ideal performance, while this the real performance of an engine, heat engine. Similarly for COPs, we can rewrite it in terms of T low or T high, or first write it in terms of Q low or Q high, then write it in terms of T low or T high. Let's see that. For Carnot refrigerator or heat pump, let's talk about refrigerator. So we have T low, T high. This is the minimum temperature, maximum temperature. Q low and Q high, Wn. Again, work in plus Q low equal Q high. Exactly the opposite of heat engine. Exactly the same as heat pump. In this cycle, COP, as we discussed before, is output over input. Output over input. What I want is Q low. I want everything in the refrigerator to be cooled down. This is Q low. This is my output. I pay electricity. Every month, you pay a bill, electrical bill. That's what you pay for. So QL over W net N, which again, Q net is Q high minus Q low. So Q low over Q high minus Q low, which is divide everything by Q low, it will be 1. Q low over Q low is 1. Q high over Q low. Q low over Q low is 1. Now, if you are talking about ideal, replace this by T high over T low. So this is the real. Ideally, it's 1 over T high over T low minus 1. Ideally, T high over T low minus 1. This is ideally. Remember. Remember, this only valid for ideal, Carnot. Also, this temperature should be in Kelvin. Do not substitute anything if you are talking about SI units, anything other than Kelvin, not Rankine, not Fahrenheit, not Celsius. If you are talking about the British units, Rankine, not Fahrenheit. We have finished chapter 6. Now we're going to go to chapter 7, which is entropy. Entropy, it says how much your losses is, how much you dump heat outside in ambient. So Clausius said that you have Q over T, which is Q high over T high minus Q low over T low. So if you are talking about ideal case, this is 0. But in reality, it's negative because you dump more heat. So this term is bigger, negative. Q high, 100 joule. You dump ideally 30. So it's 70. But over T high, actually Q high over T high, this, without this, it's 30. But now we divide by T high and T low, that's now equal to 0. But because you dump more, in reality, it's lower than. So this is reversible, this is real, lower than 0. You dump more heat in ambient in the second or lower 0 for heat engine. Similarly, for refrigerator or heat pump. This is called Clausius inequality, lower than or equal 0. Entropy is this property. is integration of this. Delta S generated for a system is delta S system, which can be more than one component, as we'll see in the midterm, plus delta S surrounding, usually one term. So we can, if you have two components, delta S component 1, delta S component 2, plus delta S surrounding must be greater than or equal 0. So the net entropy generation is this. So delta S, integration of Q over T. S is a property. So if you're talking about any property, if you start at this point and end the same point, delta U is 0, delta V is 0, delta S is 0. But the work is not 0. The heat is not 0. But the integration of delta Q over T is 0 for a cycle, complete cycle. Go here, end it here. That's why S is a property. Remember, I will say it now in the exam. When you start at a point and go to back to the same point, which is cycle, the change in any property is 0. So S or delta S is integration of delta Q over T. Delta because it's inexact. So this guy can be positive, negative, 0 for a system. It means heat addition, heat rejection, adiabatic. But this guy is a property, delta Q over T. This term, if you have temperature is constant, for example, you used to say delta S equal Q over T, this constant temperature. Let's say it's T0. So it's T0. For example, thermal reservoir, ambient, ocean, Q over T0. If we have two things together, reversible, adiabatic, like for example, Carnot cycle, process 2 to 3 or 4 to 1. It was a reversible and adiabatic. This means isentropic. Delta S is 0. Entropy change. For incompressible substance, like for example liquid and solid, delta S, as we did it in the lecture, is MC ln T over T. If you have a water, and it's water, and you give it some heat, goes from 30 to 50, 30 to 70. MC ln T over T is how much entropy change for this substance. Delta S, actually, if you remember also, Q is MC delta T. This is how much heat you paid to raise from 30 to 70. MC delta T, T2 minus T1. But ln is how much entropy. If you cool it down, it will be negative. Ln, something lower than 1, is negative. If it's greater than 1, it's positive. It means you add heat to the system. Entropy increases for the system. So locally, entropy can increase or decrease. But overall generation must be greater than or equal to 0. For ideal gas, we started from the main two definition of delta T delta S. T delta S equal CV delta T delta U. Actually, we started with T delta S equal delta U plus PDV. We have another form in terms of H. We finally reached to delta S equal CV ln T2 over T1 plus R ln V2 over V1, or CP ln T2 over T1 minus R ln P2 over P1. So we have two formulas for the change in entropy for an ideal gas. If you have temperatures and volume ratio between two states, you can get how much it changed in entropy. Remember, if the entropy, if this process is isentropic, you can put it 0. And we got another equations. Delta S, Cv ln T over T plus this, it's if you have the two states for ideal gas, PV equal RT. This is always correct for every single state. PV equal RT or PV equal MRT. We can put this in terms of volume per unit mass. So these guys always correct for single, for ideal gas, only ideal gases. These equations always valid for ideal gases. But if it's isentropic and also gas, PV to the K equal constant, or PT to the K minus 1 over K equal constant. It's called isentropic relationship. So you need to distinguish between steam table, incompressible substance, and ideal gases. These are three different things. And of course, the first one, which is Q over T, if the temperature is constant for the surrounding, or isothermal reservoir. Reversible steady work, the work always PDV. Work per unit volume, P delta V, specific volume. This is always correct. Closed system, open system. But for reversible steady flow, open system steady, the work, this one, always for this one, W is equal to reversible minus VdP. Minus VdP, only for open system and reversible, VdP. The work equal VdP again, for example, like pump. The pump, the volume is constant, so it's P2 minus P1. So you can say the work I paid in a pump, which is almost incompressible, constant specific volume, just delta P times V. Unlike closed system, when we said if the pressure, if the volume is constant, the work is 0. If the pressure is constant, it's BdV. This is something else. Now we're talking about open system reversible. We have efficiency for turbine and compressor. Turbine efficiency was, if this is the pressure lines, you go from 1 to 2, S and 2A. Always efficiencies shorter over longer. This is compressor. This is compressor, this is turbine. The pressure lines always diverging. I want to compress from P1 to P2. P2, 10 atmosphere, P1, 1 atmosphere. I want to have pressure ratio of 10. I can go vertically with 0 entropy increase, isentropic, or in reality, we have some friction, we have some heat, we have some irreversibility. So here, the work ideal over double actual, which is in terms of first of thermodynamic, H2S minus H1 or H2A minus H1. This is the compressor. This is the compressor efficiency. For turbine, it's exactly the same, short over longer, but now I get less than what I supposed to get because I have some losses. So it's H1 minus H2A over H1 minus H2S. You can start with 2S minus H1 or H1 minus 2S. But remember, if this is start with H1, start with H1. Here, the state 2 bigger than state 1. Here is state 2 lower than state 1. Because this is expansion, this is compression. Again, delta S generation is equal to delta S system system can be many things, can be ideal gas, steam table, incompressible substance. Delta S surrounding, which is usually Q over T, because usually surrounding is thermal reservoir, so the temperature does not change. Delta S surrounding is just Q over T, because temperature is constant. For any system, if delta S is negative, it means it's impossible system. Delta S means need to be 0 or more. 0, ideal, reversible, and of course adiabatic. And more than 1 means you have some losses, you have irreversibility, you have some heat in the system. Now we're done with reviewing chapter 5, 6, and 7. We're going to go ahead now to solve midterm 2, which is 6 problems. Last year, it was 60 minutes. We have almost the same contents or a similar contents with different numbers, different ideas. Maybe a similar idea, but input became output, output became input. So you need to make sure that you understand them. Remember, lecture problems are important. Lecture 11, problem 2 and 3. Remember these problems. Remember every problem we have in a lecture from 7 to 13. You can get any one of them. Chapter 5, 6, and 7, midterm 2. This Monday, August 3rd, 2020, from 11 to 12, 11 a.m. to 12. You have homework 3, 4, and 5. These are the homeworks included in the midterm 2.